Okay, physics students, welcome to the third video in 4.4 wave behavior. And I'm going to talk about, this is sort of an introduction into the interference patterns of light. We've talked about the way that water waves interact especially and how they make these really cool interference patterns. It turns out if you have a very nice understanding of that, understanding the interference patterns of light won't be too difficult for you. This particular video will be a sort of springboard into a much more complicated and extensive video, which will be my next one, on double slit and single slit diffraction. Okay, so I'm just going to talk generally about how waves interact and interfere, in particular light waves. Okay, so if we consider two wave sources having the same wavelength and the amplitude from source 1 and source 2 as shown here, and they arrive at a point P in phase. Okay, so they start off in phase. Okay, each of them is emitting a crest at the same time in a trough. They have the same amplitude, same frequency, same wavelength. Okay, arriving at point P in phase, which means that the phase difference is 0. This means that the crests always coincide with crests at P, and the amplitude of the resulting wave at P is 2a. Now, the only difference between these two waves is that the path length between their source and this point P is different, okay? And there's something very special, as you can see, about the that length. In this case, the relative length between them is such that the crests line up perfectly, as do the troughs, when they arrive at P all the time. And if that happens once, it's going to happen constantly because they have the same frequency, wavelength, and amplitude, okay? So, although they are at different distances, call them L1 and L2, their waves overlap constructively at P. You notice in this case, L1 minus L2 equals 1 wavelength. So in this particular case, it's 2 1/4 and 3 1/4. The difference between them is going to be exactly 1, okay? Now, just to point out something really quick, which may be an issue for you, notice that L1 minus L2 in this case is actually negative 1 wavelength. We don't really care about the negative because we're just talking about the relative difference between two path lengths in this section. Now, it turns out that when waves are in phase, generally speaking, constructive interference results when path lengths differ by an integer number of wavelengths. So we have this really cool relationship, L1 minus L2, or the absolute value of that, if you wish, is equal to n times lambda, where n is an integer 0, 1, 2, 3, 4. And remember that a difference in path length of 1 wavelength means that the phase shift is 0. Okay? All right, so you can guess what we're going to do next. We're going to talk about destructive interference. Now, if I vary the lengths of these two path lengths in just such a way where the crest from one source always overlaps with the trough of another source, you can see the crest of source 2 is arriving at P exactly when the trough from source 1 is, and that's because they have a very specific set of path differences here. They're going to arrive at P completely out of phase. Now, I should reiterate that they originally started in phase, right? So source 1 and source 2 are emitting crests and troughs at the same time, right? But they are arriving differently at point P, not in phase, completely out of phase because of the difference in path lengths, okay? So in this case, the crests always coincide with troughs when arriving at P, and the amplitude of the resulting wave is 0. Now, sources 1 and 2 are at different distances from P, and their waves are overlapping destructively, since it turns out that the path length difference, L1 minus L2, is a half a wavelength, okay? Here, in this case, it's 2.75 and 3.25, right? Now, generally speaking, and this is a little more complicated than the case of constructive interference, when waves start out in phase, destructive interference results when the path lengths differ by any odd integer number of half wavelengths. And I want to show you an example of what I mean. So it's L1 minus L2, or again, if you like, the absolute value of n plus 1/2 times lambda, where again, n can be 0, 1, 2, 3. And remember, a difference in path length of 1/2 a wavelength means that there's a phase difference of pi, okay? Now, what do I mean by any odd integer number of half wavelengths? Well, look, if n equals 0, L1 minus L2 would be 1/2 a wavelength, okay? If n equals 1, it would be 3 times 1/2 a wavelength. 3 is the next odd number. If n equals 2, it would be 5 times 1/2 a wavelength, okay? 5 is the next odd number, and so forth. So usually what I do when I'm solving such problems, dealing with destructive interference or constructive interference with differing path lengths, is I often write out these little fractions off to the side, so I can immediately recognize if path lengths as given in a problem are going to be one of these sort of magical destructive interference differences. Okay. So again, for two wave sources at distances L1 and L2 from a point P, constructive interference occurs when the path length difference is an integer multiple of the wavelength, destructive when it's n plus 1/2 multiple of the wavelength. So for consistent constructive or destructive interference at P, the two sources must maintain a constant phase relation. This is what we mean by coherent sources, okay? So they're always in phase. So an example of a coherent source, which we see a lot in the lab, lasers. And lasers can be different colors. You know, the ones we use are typically red, but they can be different colors, meaning they have different frequencies, okay? Now, examples of non-coherent sources would be your ordinary lamps, like incandescent lamps or fluorescent lamps, okay? So you're not going to see interference patterns from non-coherent sources. You're going to see interference patterns from coherent sources. It's very, very important, okay? And it turns out that they also need to be monochromatic or all the same color or all the same frequency, okay? Okay, so let's try an example here. So two separate coherent sources produce waves whose wavelengths are 10 centimeters. The two waves spread out and overlap at a certain point. Determine whether constructive or destructive interference occurs at this point under the following conditions, okay? So you can just do the test, all right? So again, here's what I do. I always write out this set of odd integer multiples of 1/2 wavelengths, okay? In this case, using this number right here, this is what I get. So in the conditions for constructive interference, in A, you can see that L1 minus L2 is 0.2, which of course is 2 times the wavelength, so that's constructive. For B and C, they're both destructive because notice that one is 3/2 lambda, the other is 5/2 lambda. So when you're doing the math, remember, it's really nice to have this set written over to the side with maybe the real numbers too in terms of what's given in terms of the wavelength in the problem, okay? Okay, now proof of this. I'm going to try to prove this to you in kind of a real world kind of way, okay? So if you consider waves from two coherent sources shown having the same amplitude and wavelength and frequency, okay? And as always, the circular lines represent wave fronts. So if we consider them as crests, okay? You note the wave pattern of constructive and destructive interference, okay? So for example, along this line right down the middle, you can see that crests are lining up perfectly. So those at that line, and they make a line because of the symmetry of the situation and the way that those circles go out, right? Those waves are really big, okay? Here along point P, they're also really big, okay? Here, halfway in between, they're not very big. In fact, there's no wave at all. Okay, so for points P and Q, what we're going to do is we're going to measure the distances from sources 1 and 2. So, for example, in Q, again, there's no wave at all because a crest is overlapping with a trough, and a trough is exactly halfway between two crests. And at point P, there's going to be a very, very high wave or constructive interference. Okay, so check this out. So what I did was I actually printed this slide out, and I measured using centimeter, just a centimeter ruler, okay? And I found that the distance between successive crests was about 0.7 centimeters. Okay, you can use whatever units you want. Okay, so here's my table where I'm writing out the actual magical distances with respect to the wavelengths that would give me destructive interference. Okay, and I just went through and I measured the distance between S1 and point P, S2 point P. I did the same thing for Q, and check this out. It's super cool. All right, so from P to S1, I got that it's about 10.2 centimeters. From P to S2, I got about 10.9. Guess what the difference is? It's about 0.7, which is the wavelength. So therefore, that's constructive. That's an integer multiple of the wavelength. Okay, really cool. And for Q, I got from Q to S1 was about 8.8, and from Q to S2 about 7.8 roughly. And I'm not trying to pull a fast one on you. You can actually go and measure these two, all these distances yourself, and you guys can pick any points you want on here. In any case, for point Q, the difference is 1 centimeter, which is about 3/2 lambda, which means that is a point of destructive interference. So this actually really works. This is like real world stuff, okay? And in the next video, what I'm going to do is I'm going to basically build on this foundation of this slide, and we're going to talk about double slit diffraction and single slit diffraction, which is light passing through very, very narrow openings, and what happens on the other side.